Welcome back. And here we are at the sixth session for today. And things just get more interesting. So we have, firstly, to recognize our platinum sponsors, Edge Impulse, Habana, also our gold sponsors, FNX, Lattice Semiconductor, Mind, Body, Think Silicon, and especially Lattice Semiconductors, because we have Hussein Osman here from Lattice to tell us more. Okay, Hussein is a marketing director at Lattice Semiconductor. Hussein is responsible for the ICE40 FPGA product line and developing solutions for consumer market segments as well as wearable devices and consumer IoT. And if you know anything about Lattice Semiconductor, you know they do low power, small footprint devices very, very well. Hussein has over 15 years of experience in semiconductor industry. He has worked as a system engineer in touch, capacitive sensitive fingerprint USB technologies. He's an avid sports junkie. He's played soccer for NCAA at Cal Poly. And during the video, you may occasionally hear a 2-year-old son screaming in the background, but don't worry about that. He's probably going to be a better soccer player in the end anyway. Hussein is a mentor for many engineers at Lattice Semiconductor. He's received a bachelor's degree in electrical engineering from California Polytech State University in San Luis Obispo. Hussein will be presenting for us on Lattice sensAI. It's a flexible, easy-to-use machine learning solution based on Lattice's seminal low-power edge parts. And I'm very excited to see what Hussein's presenting to us. I know he's got a kick-ass video at the end that's really compelling. So I urge you to look forward to what he's presenting. Just one quick reminder, we will be taking Q&A during the sessions. So please go to the Hoover interface and enter your questions. We'll be relaying those questions live to the presenter during the talk. And then after the session, we'll be switching over from the pre-recorded to the live Q&A. This is live, so you do have to scroll down and click on that on time, otherwise you'll miss the Q&A. All right, and with that, let's get going.
Hi, my name is Hussein Osman. I'm thrilled to be here at the ValleyML show and excited to talk to you about Lattice sensAI, a flexible and easy to use machine learning end-to-end solution. For today, the agenda that I have planned for you is going to start first by talking about the Edge AI market trends and drivers. Then we will talk a little bit about why FPGAs or edge computing. Then we'll dive into sensAI solution stack. Lattice provides solution stacks, which are solutions that include IPs, software tools, reference designs, and demo to enable users to easily use and adopt our solutions. At the heart of sensAI is the silicon, and the silicon that is that we're going to focus on here is our latest Nexus platform and a device called Crosslink NX specifically. Then we'll dive a little bit into the target applications and use cases. So let's get started. So, I mean, obviously we are seeing a significant move of computation that happened a few years back at the cloud to the networking side and to the edge. A lot of those are driven by, or the availability of compute on the edge device is driven by the fact that latency for some application requires to be very exact. It needs to happen, the task needs to happen quickly. Security, privacy, and bandwidth limitation all play factors in why edge devices are adding compute right at the device. In fact, API research says that about 60% of all the IoT edge devices that are going to be shipping by 2024 will have some edge AI capability built right into it. So that's a significant number of devices. And you know, digging deeper into the drivers of this is, designers have choices now when they're looking for an edge AI solution. There are many processors, FPGAs, ASICs that have some sort of AI capability that the system designer can go and leverage to get their job done. A lot of companies are starting to figure out how to take advantage of data, and there is lots of data that's being generated right on the edge, say a factory floor. So in order to drive actionable analytics, you need to be able to filter this data and limit what is actually taken out of this data. So that drives more and more devices to have some sort of edge AI capability. The resource efficiency on the edge devices. So a lot of the edge compute devices now are capable of significant amount of AI processing that previously used to only happen at the cloud, on the cloud side. This is because models have become better, they became more compact, they still have very similar accuracy to the larger models. More and more processors and AI accelerators are coming out. So lots of innovations that are driving the resource efficiency of edge devices. Finally, one of the main drivers is the ambitions to create an edge to cloud solution. An end-to-end solution is going to be a smarter solution that allows the right processing to occur at the edge versus the other processing where more processing capabilities needed to be moved to the cloud. So a lot of drivers around edge AI and the move to the edge. When it comes to silicon options for edge, for designers that building an edge IoT device, for example, they have many options to choose from. You can choose a CPU or MCU that has AI capabilities. They can go with a powerful GPU. They can pick a efficient FPGA, or they can find an optimized ASIC to take care of their solution. Before I go into why FPGAs, just wanted to give a comparison between GPUs, CPUs, and FPGAs for those who are not, they don't know much about FPGAs, for example. So a GPU is known for graphic kind of processing. It's been used for ML processing on the cloud, on the server side for the last decade or so. A GPU has many not so powerful cores, but it has many of them, and so it can take care of a single task, same task in parallel, exactly same task, but in parallel, multiple of the same task in parallel together. So it's high performance. It does have a cost of high power, and latency it is not always the best with GPUs. CPUs in the other side have few cores that are very powerful, and they are serial processors in nature. You have a clock, you have an instruction set, and you execute one instruction in every clock cycle. And so they're somewhat fixed hardware. You get what you pay for. You know exactly how they work. They are used heavily for ML today. They happen to be not the most efficient way to go about things. So FPGAs on the other side are not fixed hardware. They're hardware that is blank. You get it, you program it, you make it into what you want it to do. You can implement an entire application end to end on an FPGA. So some pre-processing, some AI, some post-processing, ISP function for computer vision. It's really optimized and it's an efficient way to do things. It does come at a cost. You need to know how to do some of the programming, RTL, some hardware descriptive languages in order to take advantage of an FPGA. But that's where a lot of FPGA companies, including Lattice, are putting together capabilities that are similar to sensAI and providing ways to solve the access issues that software teams are not able to use FPGAs by providing a software-based solution to enable their devices. Looking at Lattice FPGAs specifically, and as we went in adoption of AI and edge devices, it became clear to us why FPGAs are really the right choice for some of the applications at the edge. So power consumption and power consumption, Lattice has a range of devices that can start all the way at a milliwatt and can go up to close to a watt. And these come scalable performance for that power envelope. So the ability to get a lot accomplished at those power levels is something that it's not in any other device, an ASIC or CPU or GPU. The flexibility of the computational resources, the FPGA comes with DSP blocks, it comes with lots of memory, it comes with computational blocks, and you have the capability to put together an entire end-to-end solution within the FPGA. On the top right corner, the scalability of performance to handle multiple use cases, and later on I'll talk a little bit about how you can chain multiple neural network, each one of them taking or doing a specific application. The security features that are available in an FPGA, a lot of FPGAs, including Lattice's FPGAs, have a security block that allows only a authorized bit stream or design to be loaded and to authenticate and allow the user to come in and update. Only an authorized user can update that bit stream. And then the most important piece is really the hardware programmability of the FPGA. And I'll talk a little bit more about that in the next slide, which is FPGAs are, as I said, a blank canvas. You can create what you would like the device to do. With the parallel processing capabilities of the FPGA, they are well positioned to deal with the fast-moving world of AI models. It seems like every week or every day there are new innovations that are coming out in AI models, and you have the ability to go change RTL very quickly and adjust the acceleration engine to meet some new layer or function that is required for a new model. So this hardware optimization, that when it's put together with the moving algorithm and optimization that are happening on the algorithm side, that creates a way for system designers to introduce continuous improvement and add new use cases, reduce power. So the hardware programmability of FPGAs, in my mind, is the key for why they're well suited for fast, rapidly changing technology like AI. So Lattice sensAI. What is Lattice sensAI? Lattice sensAI is a solution stack. As I said earlier, it's built around 3 device families currently that Lattice supports within the stack. On the left-hand side in the bottom is ICE40 Ultra Plus, this tiny 2.0 by 2.5 millimeter square FPGA that has enough power to get things like face detection, AI use cases completed within it at 1 to 10 milliwatt, depending on how fast you want to run it frames per second wise. It can run a mobile net V1 model pruned for the device, of course. In the middle is the Crosslink NX, and the Crosslink NX is a family of FPGAs, and it can do object detection, object counting, object classification type of applications. and it ranges based on which family member you choose between 50 and 200 milliwatts. And then we have ECP5 family of FPGAs that does between 250 and 850 milliwatt. And I'll give you example what type of networks and applications and you can accomplish with each one of those devices. For each FPGA, we have hardware platforms that can rapidly allow somebody to develop something, an application, an edge detector, a camera, something that, you know, with all the pieces are built to the FPGA into the board. The next level up on our solution stack is a neural networks, the accelerators for neural networks. These are RTL engines that are accelerators, pre-built, ready to go. They focus, they're, you know, built for devices. So depending which device you looking to use, you find an accelerator that works for it. Obviously, they're optimized for the device. They take advantage of the resources that are available within the device. On top of that, we have some software tools. You really can't sell silicon any longer. You need to sell with the silicon some software tools to allow somebody to do something with your device. So we have a compiler that hooks up to Caffe, TensorFlow, TF-Lite, or Keras, and compiles a set of instructions and weights that our FPGA or the neural network accelerator understands. The other tool that is impressive is our sensAI Studio. We put together a tool that allows you to train and test models and deploy them into edge devices. Propel is our FPGA tool for building SoCs, so you can build a RISC-V based SoCs, and you can instantiate an AI accelerator engine that can be used for some of the AI use cases, and a RISC-V processor that's used for other general purpose processing and assisting the AI processor. And then Diamond and Radiant are our FPGAs design tools, things you use to, you know, input RTL into it and end up getting a design that's loaded into the FPGA. We've designed many demos or reference designs over the last 4 years since we introduced sensAI, and here are some of the examples that we have, and we'll talk a little bit more about that in upcoming slides. We have some custom design services. So with FPGAs, when we normally show up to leading technologies first, because silicon is already available. And so we really needed to do a lot of education, telling customers what they can do with our devices, what are the target applications, how they can differentiate their devices, and to do that, we needed to put together some type of you know, a trainings and design services that we can help them go to market quickly. This is the design methodology for sensAI. We provide neural network models, example training data sets, so a designer can look at how we label. Labeling is key for edge application with devices that are more constrained than a GPU running on the cloud. We provide, you know, easy training scripts that allow somebody to go through one of the frameworks and output a trained model, and then bring that into our compiler tool and create a set of instructions and weights that interact with the design that's sitting in the FPGA. The design that sits in the FPGA use tools like Radiant or Diamond for Lattice, and you can instantiate sensor interfaces. So whether it's a image sensor or microphone or something else, you can instantiate the neural network accelerators. You can instantiate pre-processing blocks, ISP, post-processing block, and a host interface if you want to interface to the system, to an SoC within the system that the AI task being done is being offloaded off of that. There is a lot of flexibilities in terms of IOs, and there is flexibilities in terms of the type of interfaces that you can implement within the FPGA fabric. So this is a high level summary of what the design methodology is, and this is a hardware centric design methodology. So it's really optimized around the hardware. There are no processors that are instantiated within the FPGA. So next, I want to talk about Crosslink NX, and this is our latest Nexus family of FPGAs. Crosslink NX is a 28 nanometer FP-SOI. So when we built this device, we were thinking about low power. It's elite in terms of power performance for FPGAs. You get the goodness of the high performance on video and computer vision AI at power levels that are basically 1/3 or 1/2 of what other FPGAs are capable to do. So just a quick comparison, taking NX40 and looking at comparable MCUs that are trying to do specific tasks, and looking at our previous generation devices, basically the Crosslink NX does 12x faster in terms of performance over similarly priced MCUs that are doing similar tasks to us, and it does it at essentially 1/3 of the power the MCUs are able to do, and the performance is driven by the ability to do compute in parallel fashion, and the power is driven by that because you end up doing multiple tasks together at the same time, and then you don't have to do these tasks at high frequency, which just means lower power overall. A closer look at the NX family. There, these devices, as I said, is an FD-SOI 28 nanometer. It's designed with low power in mind. It does have additional capabilities to set up the device in low power mode or high performance mode, depending on the system needs. It comes with lots of embedded memory. So AI and memory was in our mind as we built this device. It has dedicated DSP engines that can be used as multipliers. It has hardened MIPI PHYs to bring in data as fast as possible at 2.5 gigabit per lane, 4-lane, 2 MIPI PHY hardened PHYs, and PCIe out to the SoC. There are plenty of other IOs to connect other sensors or to interface to external memory if you wish to run a larger model. One more important feature about the family is the fast instant on capability of this device. So within 14 milliseconds, the device can go from unconfigured to configured, essentially not missing a frame in a 60 frame per second video feed. As it's coming through, it's able to wake up quickly and process that. So system designers, if they wish to reduce power consumption even more, they can turn the device off and turn it on once in a while to do some processing, once in a while being a fraction of a second. So as I said, we really paid attention to memory and amount of memory, and we know for AI application, having DDR memory externally it's a power hit every time you need to access weights that are stored externally, or if you store a frame for computer vision type of application externally. For processing that's happening, going out and coming back, it's an inefficient way to do things. We included large memory blocks. There are multiple 5 large blocks of memory that are positioned well for use along with the DSPs and the logic. We also have EBR memories. These are memories that are distributed throughout the fabric, and essentially they're used for local storage and scratchpad operations. So the way FPGAs are built is really done for AI, and it works really well for AI and AI workloads. Earlier, I showed you a design methodology that's focused on a software or hardware-centric way. It does give the best performance for an FPGA, but we know that there's a lot of users out there that just don't have the RTL capability. So we looked for ways to simplify things, and we created a software-based methodology where a TF light model can be converted to C++ and brought into our Propel design tools to put together an SoC that has a RISC-V. It has a security blocks. It has ML accelerators. It has vision accelerators, an ISP, and the goal is to trade off power consumption and ease of use for performance. So the hardware-centric solution, it's the highest performance solution when you compare it to this. And here there's a RISC-V, and RISC-V slows things down. And so the solution is a little bit slower than our hardware-based solution. But it's a lot simpler to use, as you essentially have an SoC with a processor in the FPGA fabric. I am now walking through the sensAI stack. So now I'm talking about the accelerator engines that we have. An example of the accelerator engine is the CNN Plus accelerator. Just to give you a feel for what blocks are there with an accelerator. So there's obviously convolution engine, given that we're supporting mainly CNN type of models, fully connect engine, and pooling engine, a ReLU engine, a scalar engine. So the major needed block in order to put together a network, some of the popular networks out there. And we connect memory blocks to the engine in such a way that it's the memory usage is optimized for how the engine would access this data. So this Syn accelerator engine is able to be configured in different modes. You can put it in a mode where it's in low power. You can put it in a mode where it's in high performance. And it supports a variety of neural networks that are out there: MobileNet, V1, V2, SSD, ResNet. We have examples of all of these networks through reference designs and demos, which I'll talk a little bit more about. There is a number of optimization the user can choose from, and so we'll start with memory optimization. These are all related to the accelerator engine. So the user can choose different assignment of memory. Basically, choose where the blob will sit, and for a computer vision application, blob in, blob out firmware on the internal RAM of the FPGA, and then have the entire flash external to the FPGA filled with the firmware for the ML application. There are two other alternatives here, where on far right is the firmware is completely stored on external flash, and then the internal memory has blob in and blob out. So depending on power constraints, the type of network the user has, there are some things that can be done, and the neural network compiler can be used to kind of set up how the memory is optimized and used. Other optimizations that we look into is how to have the entire system within the FPGA and then only turn on pieces of the pipeline as needed. So while capturing audio or capturing video, the ML engine doesn't need to be on, and you can save power by doing those type of things. So turn off the clocks from pieces of the design that are not needed while other pieces are on. So having that knob to be able to do that as the application is running saves quite a bit of power. And finally, there's the ability to optimize how many networks run. You can literally store multiple use cases within an external flash, and as the engine runs, you can point it to which network to start running, or you can instantiate multiple engines and have each one of them running different applications from flash. There's some flexibility definitely in terms of chaining together multiple networks, chaining together multiple applications, and running them at the same time. So with this, I'm going to go to the next layer in our stack, which is the tool, the compiler. It's really the central piece of how you take a neural network design that's been developed, analyze it, figure out which device it fits into, compile it, and push it into the target FPGA. So it's a graphical interface based tool to make taking a trained model and using it for one of Lattice's FPGA as easy as possible. We also went a step further and we created what we call Lattice sensAI. Lattice sensAI is a tool and where you have a model zoo of different models that are already pre-designed and optimized for our FPGAs. You can choose one of those models. You can go through transfer learning, since most of them are already trained for a specific application. And I'll talk about what possible applications are there. You can capture additional data and bring it in, train, optimize, configure how things are going to run, share a dashboard of how trainings are running with other users who are working on the same job at the same time, and then compile for a specific FPGA, evaluate how the design works, and push it into a device and test it in hardware. I've seen customers that have a data set, they want to understand how to quickly get moving. They pick up our hardware, they pick up this tool, they bring their data set, pick up a model, and within a few days, they're up and running, trained, and doing detection that they're looking to do. So we try to simplify things as much as possible, and this is one example of those tools. Speaking of hardware, one of the FPGA boards that is available to quickly prototype a computer vision or audio type of use case is the Crosslink NX VVML board. It comes with onboard 2 image sensors, depending on what the user is looking for, high quality versus a low power. It comes with multiple microphones, expansion connectors to connect to different sensors through PMOD. So trying to leverage that ecosystem and the sensor capabilities that they have. And then there's a USB out video over USB possible through that USB controller. So it's an end-to-end evaluation platform that allows somebody to go try to do some detection by pointing the entire board at the items they're interested in detecting after they used sensAI Studio to train a model and deploy it onto the device. So now I've kind of walked through the entire stack. You've looked at hardware, you looked at IP, or the engines, the software tools. Next time I'm going to talk a little bit more about reference designs and demos, and we have plenty of those. We target applications around presence detection, object classification, and object identification. So some example applications that we've had success with here. And generally, the presence detection is a very tiny network that's looking for an object of interest, and then it triggers something else that possibly can be an SoC or an application within an FPGA where it's classifying a number of objects, which is popular for things like robotics. One of the other use cases is object identification, We use one-shot learning, and we have a network that is able to extract features from a device and compare it to pre-registered features of previous devices being pre-registered. Thinking about FPGAs and especially the type of end applications we end up, I find a lot of the end applications are not only using the FPGA for ML, but they're using the FPGA for something else, whether it's sensor aggregation or motor control or some security purposes. And then in addition, FPGAs are end up being used for the ML workloads, the AI workloads. So it's important to provide a system solution for multiple things, not to just come into and solve one problem. That's one approach we find to be very effective. So some of the reference designs, and I'll go through those a little bit quickly, are things like human presence detection. And here are some of the applications where we end up doing some of the human presence detection. We can be done on an ICE40 Ultra Plus, the 2 by 2.5 mm device that I discussed with you earlier. The input resolution is 160 by 160, so it's sufficient to detect a person from 2 meters away, and not only detect them, but understand if they're intending to use a device or not. The same device can do audio wake word and detection at between 800 microwatts for voice activity detection, and then 7 milliwatt for the actual keyword detection. Some other applications, gesture. Again, these 3 applications I talked about is around our lower power FPGAs, ICE. And here it's 64 by 64, so it's able to detect the person or a gesture probably 75 centimeter away from the image sensor, and some of the applications that are enabling by that type of solution. As you get into the little bit higher performance application, Crosslink NX family is where the best fit. And you can get an impressive QVGA through the device processing that at 48 frames per second at 200 milliwatt. So that's really why we the efficiency of the FPGA and the capability of performance that you get out of it. It's a really impressive ratio here. On our ECD5, that that device can do more of the identification, so the robot identifying the main user, or a printer identifying the user as the user is walking up to it, using computer vision for both in both cases. And that is done at 224 by 224 RGB, 850 milliwatts. So a number of use cases that are flexible, they use different FPGAs that we have within our arsenal of devices, and the performance to power capability are really great. The entire application can be done within the FPGA, so that capturing MIPI interface to the image sensor, bringing in the data, an ISP, an accelerator, a post-processing block. A lot of the ASICs that you see out there, even within GPUs, you see a TOPS number that is really high. In a lot of applications, you really cannot hit that sustained marketing number for TOPS, because the pre-processing and the post-processing blocks are running on CPUs at the end, and they end up slowing the overall application, even though the accelerator is fast enough. You have to pre-process the data and post-processing. So an FPGA would be able to do the entire process, the entire solution in an optimized way, end to end. So we have some data here for comparison between our devices, the Crosslink NX17 and the 40K. The 17 has 128 kilobyte of internal memory. The 40 has 256 kilobyte of internal memory. And you can get 320 by 240 QVGA, 38 frames per second, all the way to 160 by 160, 64 frames per second on the 17, the smaller family member, Crosslink NX family member. And as the designer can choose larger devices on the 40 side, you can get up to 72 frames per second, 160 by 60, 160 by 160 processing, or QVGA at 48 frames per second. So that's from a memory side. On a DSP side, the smaller device has 48 DSP multipliers, 8 by 8. And the larger device, the 40K LUT, has a 84 multipliers. And so a VGG can run at 224 by 224, 48 frames per second on the larger device. And it can run at 32, the same network runs at 32 frames per second on a smaller device. Next slide is basically going to talk about the trade-off in network and optimization. So we'll spend a lot of time putting together a number of networks that can be taken and deployed into edge devices. And we've had some significant success with customers since we've been working on this for now a few years. And so the system designer can choose to go with a 48 frames per second, 300 by 320 by 240 QV or QVGA design, or can choose to go with a 38 frames per second QVGA design. And the difference is the network is pruned slightly. There is a loss in accuracy of 2%, but 20% increase in performance. So the time that we put in to build the networks that are optimized for the device makes our solution easy to use, flexible. The tools like sensAI Studio are a quick enabler for a user or designer to get to market quickly. Before I end my talk, I just want to give you a quick demo, and I will run a demo on Crosslink NX here, a video on the next slide.
Hello everyone. What you see here is a development board equipped with the Crosslink NX FPGA based on the new Lattice Nexus platform. The FPGA has been programmed to perform human presence detection and counting, which is a common AI use case found in many applications. As you can see, there is a bounding box around the upper half of my body indicating that my presence has been detected and my movements are tracked as well. Next, I would like to invite a couple of volunteers to stand in front of the camera. And you can see that all three of us have been detected and the count has been updated as well. So all this functionality is being implemented at half the power consumption and double the performance of the prior generation solution by utilizing the advanced architectural innovations of the Nexus platform, including the addition of the large RAM blocks and the faster fabric performance. Thank you for your time.
All right, so that was a quick demo of Crosslink NX40 doing some human presence detection. That's a mobile net V2 design running at 224 by 224 at 30 frames per second. So I've now come to the end of my session. I would like to leave you with some takeaways. So we have an understanding and sense that there is a lot of need for computational right at the edge devices. And I talked about the driver. And so we expect adoption to really explode over the next few years, where more and more devices are being deployed with some type of AI capability on the edge devices. FPGAs with the parallel processing capability provide efficiency in terms of performance and power that are not matched by other devices that are available. Lattice's FPGAs specifically are optimized for edge devices when you compare them to other FPGA providers in the market. We have devices that go all the way from the 1 milliwatt to 1 watt, and we talked about the performance capabilities even at that 1 milliwatt tiny i40 Ultra Plus device. sensAI, as we talked about the stack, hopefully you got the sense of all the tools and the pieces and the networks and the model zoo that's available to allow somebody to go design an application quickly. And you know, there's specific end-to-end reference designs and demos that are available for target applications a designer can go take advantage of. So I've come to the end of my session. I want to thank ValleyML conference for allowing me to talk, and thank you for your time and your attention. Goodbye.
Hi, welcome back. We have Hussein Osman here with us to talk more about Lattice's offering in the AI space. And Hussein, I very appreciate you coming on board to answer live question and answers. So have you taken care of your child and we are all okay? We're all clear?
Yes, yes, we're ready to go.
Excellent. We got our priorities, kids first. Okay, so, you know, my sort of somewhat, challenging question for you first is, okay, why FPGAs? Why is FPGA the best solution for AI?
Yeah, that's a good question. So currently, almost every other week, we see a new model, a new ways of doing things. That lends itself really well to FPGAs, the programmability of the engines that do acceleration. These are, in most cases, are done in RTL, things you can adjust in few weeks to kind of keep up with the evolving nature of AI. So that's a biggest driver in my mind. Beyond that, the efficiency of the FPGA to run an end-to-end application. The vision use case, you can have a pre-processing block, an ISP, you can have a neural network, and then you can have post-processing that all runs within the FPGA in parallel fashion. That in turn gives you the efficiency in terms of higher performance and lower power than devices that are splitting this work between CPU and a smaller or a GPU or another chip on the side. So these are the main three reasons in my mind. The ability to keep up with AI changing world, the efficiency, the ability to run the entire workload end to end within the device.
Okay, so why Lattice? Why Lattice out of all the FPGA vendors?
Yeah, so Lattice has been focused on edge compute. The devices that we've built are built with edge applications in mind. And those are all the way deep at the transistor level, the choices we're making on what process to use. So for the Nexus platform, the Crosslink NX device that I talked about in my presentation, that's built on 28 nanometer FD-SOI, a process well known for low power. So at the transistor level, we made choices to support the lowest power possible within our devices. At the architecture level of the FPGA, we've put resources in a manner, the way we design our chip, that we distributed compute, DSP, and memory resources across the chip to really provide a perfect way to run AI model and have those engines built within our with these resources to deliver an AI model and have it work on our device. So those are the choices we're making, and really that ends up with the efficiencies that we're are able to drive, the type of performance that we're able to drive are all because of these choices we're making. Lastly, I would say sensAI. sensAI is a stack that we put together that really is there to make things easy to use. Take the hard out of hardware and make the adoption of AI on an FPGA on the edge an easier task, which a software engineer who can work on and focus on the innovation on the neural network side while the hardware is taken care of.
Yeah, and from personal experience, a lot of applications I saw in video recognition, for example, based on a GPU, were actually spending most of the front end using the neural net to do essential image processing tasks, and then burning, hundreds of watts, literally, to do what could have been done in, fraction of milliwatts with ISPs. And so you're identifying one of the key strengths, which is you actually have DSP in silicon. You're not synthesizing it with CUDA. You really have it there in hardware. And so do the stuff that matters most efficiently, leveraging some of the integration. I heard you mention the flexible DSPs. What other features do you integrate inside the Lattice solutions?
At the hardware level, the DSPs themselves are built. For example, they can be divided. They're 18 by 18 multiplier units, and they can be divided to 3 by 3, 6 by 6, 8 by 8. So
very flexible.
You get the flexibility to choose how those DSP engines are going to be used depending on the model that you're going to use. So yeah, something that we really paid attention to.
What about stuff that other people normally have to spend, external, lots of challenging problems getting IP blocks? How about video, audio? What do you have?
So in terms of video, you see IP blocks for ISP, a full-fledged ISP that can run before the neural network or after, depending on how the application needs it. In audio side, we've developed demos and reference designs that are focused on CNN-based audio processing. And we definitely, transitioning that into more complex LSTM or RNN type of models that provide better accuracy than CNN models. So we've done lots of video stuff, and we understand that a device that is understands the world and context aware is a smarter device. So we're adding more sensor data, multimodal inferencing type of scenarios to provide a better user experience to the final user.
Okay. Sounds like there's opportunity there for innovation in new models to connect with you and work on how to better do natural language processing and image processing as well in the blocks that you've got. Yeah, okay. So that's a good lead for the audience, I think, to follow up there. So we sort of skipped over the big question, the elephant in the room, which is why the edge? Now, I know you, before we get to that, I know you you emphasize, why FPGAs, so I want to take a moment to think about, okay, turn that into something, really simple math. Give me an example, for example, MobileNet. How would you compare against an MCU or processor solution, which is generally more flexible?
Yeah, when I compare an MCU class device similar to the NX, for example, I see our performance anywhere between 5 and 10x in terms of frames per second on a MobileNet V1 type of architecture. And the power is about a third of the power consumption that MCU would have to do in a video type of application. What ends up happening is the MCU is spending the entire time trying to accomplish the task, and the FPGA is doing the task quickly and going into its lowest power mode and coming back and doing another iteration of the task. So that ends up with the performance and power parameters that I just shared.
Okay, so I think key takeaways from your foils then would be the price, power, performance advantage for going with Lattice FPGA solution. Okay, I get it. Okay, so we're on the edge. Why? What's the, edge has been talked about for a long time. Obviously, you've invested a lot in sensAI, making it easier for developers. There's a reason behind that, I'm sure. Why is edge so important right now? What's driving?
Yeah, I think I talked a little bit in my slides about the privacy and security aspects of why users want their data to remain right on device and not to be shared with cloud service. On the edge, you're going to also deliver fast analytic that you would not be able, and more accurate analytics that you would not be able to deliver right away on a cloud platform. And I'll give you an example, like doorbell. I have an annoying doorbell that sends me, notification whether there's a cat that goes by or a dog or it's a human. Being able to make a decision quickly on the edge device and send that information to the user when they need it makes the final product a more easy to use, more trustworthy product that you can rely on that type of security application. We've definitely been talking about the edge for a while. We finally do see that adoption happening within edge devices. These designers are looking at the cost of what it takes to run something on the cloud, and they want to own the end-to-end application right on the edge device. So the tools that are available, such as sensAI, is making it easier for somebody to go figure out how to deploy a vision application, for example, right on their edge device.
Okay. I would think you've emphasized the example of the doorbell that doesn't send the cat or the dog, but only sends the person. That's also going to translate into bandwidth, which the doorbell vendor or the user ends up paying for one way or another. Mm-hmm. Okay. All right, let's ask the other question the other way. Okay, so convinced on the, we're going to do this as an edge device more intelligently. You've given us some great data points on why it wouldn't be, say a RISC-V CPU. Now, why wouldn't it be an ASIC?
Yeah, definitely ASICs are more optimized for specific application. Again, going back to the original point that I made, AI is moving so quickly. You end up spending ASICs over and over and over to meet the application requirements. Right now, with where we at in terms of innovation of AI, having an FPGA flexibility of that ability to design quickly is really key.
Yeah, now would not be a good time to ask TSMC for a wafer start. We're making $2 or $3 million wafer start cost for an ASIC. Yes. Okay. So, great way to bypass the semiconductor shortage. Lattice has already done the hard negotiation, so you don't have to get in line at the end of the queue with semiconductor manufacturer. For sure. Okay. Kind of, at this conference, we have a lot of different people here and a lot of different types of people. What are the key things that you're looking for in this ecosystem, and what could help Lattice?
Yeah, let's say we're transitioning to audio use cases, for example. I really see collaboration with the ecosystem as an important way to innovate and continue to bring in new technologies into a flexible architecture like an FPGA. So, in this conference, I'm looking at other compiler companies, application level companies that are doing things that can be integrated into an edge device. We can work together into kind of driving that to end products and end customers. So that's a big interest of mine right now.
Okay, and lastly, Hussein, what's the best way to contact you or to contact the support for the sensAI solution? What would you recommend? Give an email or contact details?
Yeah, just my full name, Hussein.Osman@latticesemi.com. And the sensAI webpage has lots of information. It's been updated and kept up. It's a good resource to go find a lot of details of what I just talked about today.
Awesome. Hussein, thank you for coming in. I appreciate you explaining to us a lot of, giving us a lot of key insights on why the Lattice FPGA solution is so compelling for the edge. Thank you.
Thank you. Appreciate your time.
Cheers.